Thank you, Tommy. Thank you for organizing this and giving us a forum. So yeah, we'll be talking about small language models. Seems like there's a theme here today. We'll talk both about the tech and also the business reasons. But before getting into that, a little bit about us, a little bit about AWS. I'm Andrei. I've worked in games since about 2004, last 3 years at AWS, but before that in production, in marketing and analytics. And Patrick has a long and storied history in VFX, in CGI. He's worked at DreamWorks. He's worked at Jim Henson's workshop. So he's the technical implementer, and he'll talk more about like the under the hood. And I'll cover I'll lead us in and out. We're AWS. You may have heard of us. Myself and Patrick, work on the team within AWS that focuses on games exclusively, having come from games or related industries. We have many customers across the world. Many of you are probably our customers, so thank you for that. And the way we think about what we can bring to games to the industry is kind of across these range of use cases that kind of break down into things you can do to build your studio and build your game, things you need to get your game running, so servers and infrastructure at scale, and then things you need to grow your game, all the things, marketing, live ops, etc. And what we've noticed over the last year or 2 years is that while AI used to be its own separate thing, now the things you see highlighted in yellow are places where AI is having, there are AI solutions to support the use case. When we think about AWS in particular, a moment on how all the different things we offer for AI is at the top, we have some products, so things you sign up for. We have our own IDE, that's AI first. We have a Quick Suite, which is a kind of like a assistant and analysis tool for information gathering and your personal kind of like office assistance. And we have Amazon Connect for customer service, so all things CRM and call center. But the part where I think it gets interesting for many of the folks in this room is Bedrock. Bedrock is a place to run LLMs. We have, I think we're up to 250 different models on Bedrock, and they run in your account. So all the privacy and security that you're used to if you're running on AWS applies even to the LLM workloads or the diffusion model workloads. So that means like you're not calling out external APIs. You're running things, but within your walls, which is making a big difference for folks who are looking for that privacy. And finally, if you want to open the hood and start plugging things together and replugging them and building new models, there's both the infrastructure side of things and SageMaker, which is kind of like a managed general purpose ML service. So if you haven't heard of those things, I'd be happy to show you. We have a demo booth set up. A little bit more on Bedrock. So it's a place to build applications quickly. You pay on demand, so you don't have to spin up infrastructure. You just stand up your RAG database, stand up your model, choose your model, evaluate your model. We are also working on helping people develop this stuff. Setting up frameworks where it's easier to build agents, to give them memory, to give all of the things that happen outside of the LLM, browser use, etc. So I'm bookmarking a lot of this stuff for you, and we can talk about it once we wrap up today's presentation. So the recent announcement, I'll just put this up as a last sort of thing. Storing vectors can be expensive, can be large. We announced S3 vectors, basically an S3 bucket where you can drop your vector store, and it's cheaper, faster than what we're offering previously. So if you're interested in that, we can talk about it as well. Okay, so let's move on to the actual topic of today. Why are we here? We have observations in talking to customers. What we've noticed is that one, and this is probably not a surprise, running generative AI at scale is a little bit problematic because of the speed and cost of doing that. The economics, if you don't do it right, don't really work. And so what we're also seeing is an interest in doing those things. And 2 years ago, we were talking about NPCs that are driven by LLMs. And that has exploded into a number of kind of related use cases. Things like assistants, things that help players without necessarily being embodied as a game character. And so I think what we're really seeing is the birth of a generative AI model as a game asset. What does that mean? It means that now that you've built your model, you have to do all the things you do to your game assets. You have to test them, you have to version them, you have to sync them with the rest of the game. So it becomes a production challenge, if you will. So we're figuring that out as an industry. So our thesis today is you can run things on device. We know that's possible. We think there's value in doing it on a device that is not also the player device. So one of the feedback points we get often is like, yeah, I would love to run LLMs or SLMs on my device, but my device is already busy running the game. I don't have several gigs of memory to spare. So okay, no problem. What if we used another device, a phone? People already have habits of phone use while doing other things. And maybe there's a way we can harness that. So we wrote a blog on this topic, I want to say in June, and it got interest. The blog was about, it was a little bit hypothetical, but it talks about the opportunity to use your mobile phone as another input device, as another way to interact with the game. And we got, folks were reaching out to us wanting to talk about this more. And so that's why we're here today, because we took the idea further and we built a prototype, which Patrick will demonstrate, that takes that idea, makes it practical, and actually forces us to go through all the steps of making it work. So one, obviously, we're not consuming the console or the PC or the other phone resources to run the inference. Makes it easier for the game to continue running at 60 frames per second. But also, it's opt-in. So we're not forcing anybody in this business model to use the other screen, but it can be helpful to people who want to do it. And it's still integrated into the game stack, which means that you're building it in sync with the rest of the game, so it acts as a game feature the way you would do it on the device, just on a different device. So what do we have to do to make this happen? We have to find the model. We have to, well, first we had to find a game that made sense. Then we had to figure out what model we're going to use and how we're going to use it. Then we had to build a cloud architecture that makes this all work together. And then we had to build all the connections, build the actual second screen application, integrate in the game, test and measure, etc. Sounds nice. What ended up happening is we spent a ton of time on selecting and tuning the model, as you probably expect, a ton of time testing and measuring to make sure we got it right. And the actual building of the application was sort of not quite an investment. And that's kind of what brought us to the talk here. The lessons we learned in going through that selection and testing process is what we hope to share today. Fundamentally, what we're doing is taking a model and fine-tuning it to perform specific functions in the game. So any off-the-shelf model isn't going to know how to play our game, certainly not with the APIs that we just built for the project. And it's not necessarily going to behave the way we want. So one idea is to fine-tune your smaller model that can fit on device to bring it up to, for that narrow set of responses, narrow set of use cases, to the same quality you would get from a bigger model that you would be running in the cloud. And so games is not alone in this. We see other industries going down these roads. And there's research from folks here today, as well as other GPU providers, NVIDIA's written about this as well. So we definitely see this being as part of the way AI gets implemented and becomes economical in games at scale. But we also don't think it's the only answer. So more on that later. So what do we build? I think this is over to Patrick to walk us through.
Sure. Hello. So the idea is to kind of start going into the POC. We started off with taking a game that has real free licensing, which is we took an Unreal game that they provide for free, which is Crop Out. It's a very simple RTS. And the idea is that we started taking it and we added a REST interface. It was written in Blueprints, and how fun that is, writing one. But the idea of having the interface meant that you can programmatically access the game, get game state, change game state, and anyway we did. And then the idea is on a second device, we would then create this small language model. We would fine tune it along with being able to have voice as an input. It would speak back to you. And then in this demo, what you're going to see is that we're running on equivalent hardware of what a phone would, like a medium level phone would be, right? And so it's not like running on an NVIDIA machine where the system is quite capable of running these small language models. It is running on a device that is CPU only, running in around 30, 40, 50 tokens a second, right? Really limited. And so you're going to see in the playback, you'll see some delays, and it's really to show you where we are now and all the lessons we learned in getting there. So let me start here.
Come to Crop Out.
Oh, there we go. So all the REST APIs.
Hey,
right?
are we
You see within a
connected to
game,
my
would
game
you know
of
if
Crop
REST
Out?
API is called? You wouldn't, right? So it's basically all the REST APIs that are happening are appearing on the screen
connected.
in the corner as just kind of a pop-up.
All right, cool.
So you're,
What are the villagers doing right now?
so there you go. I'm asking a question, right, to the edge device. And you can see there is that little delay that we're getting when we're running on a small language model and doing all of the speech to text. And so it's making a number of calls.
I checked the villagers' current jobs and the resources available on the map. The villagers are working on various tasks, and the resource counts are as follows: 3,313 food, 3,435 wood, and 1,865 stone available.
Okay. So what jobs are the villagers doing then?
So you can see that it reached out to say,
The villagers are currently assigned to
what
the
are the
following
villagers
jobs.
doing right
3
now?
villagers
Get
are
that
idle,
information and
17
bring
are
it
working
back.
on farming, 5 are gathering wood, and 0 are gathering food or stone. 0 are building anything right now.
Okay. Let's have 2 villagers who are doing nothing. Have them start farming.
So now this is a case where we're actually changing the game state, right? We're reaching out.
Villagers have been
to the
reallocated
REST
to are now
API
working on
to
farming.
make that change. But on top of just interacting with the REST API, you now are also adding in the ability to know
what do you
about
recommend that I do
strategy
next?
about the game, given the current state, or things like being
With
able
your current resources, it seems you have enough food to sustain the village. Since you have seemed to have enough wood and stone, consider building a monument.
All of your players are really good at it, so it makes it hard.
What do I need to build a monument?
To start playing the game. So in using these kind of assistants, you can help.
You need
level
500
up
count of wood and 500 count of
newcomers
stone to
the
build a
game
monument.
and be able to get, so when they go online and start playing, they don't get.
Hey, what do I do if I want to play in the next tournament?
Right. And so the game also is, the idea is that here we're also introducing the idea is
Let
that
me check.
it's not just.
You have not registered for this season's tournament.
Right. So in this case, right, it's not just running on the local edge device. It also understands that there's a whole API out in the cloud. So if you're, in this case, it asked about a tournament, but the playing the game and in the tournament is something that you would do with multiplayer in the cloud. So it knew that it did a model selection. It chose that, hey, this is kind of this API we want to use in the cloud, and then it reached out and made those calls out to the cloud. And in this case, they weren't registered for the tournament. So you can do that differentiation, this hybrid model where, yeah, while you're playing the game and learning and doing everything, you're using the local model, and that an inference is being done on your device. But then in the cases where you need to go out to the cloud, it's there. Okay, so let's dive a little bit more. Given this crowd, we're going to go a little bit more into the technology of it. Oh, great. So what it was done here, right? So what was taken is we took the Gwen 3 1.7 billion parameter model. We fine-tuned it and then quantized it to int 4-bit, or it's using K-quants, which means it's mostly 4-bit with some 6-bit on some of the important parameters, right? And then what that meant is, on an AWS EC2, on a G6E, it took about 25 minutes to fine tune, which is less than $2 to actually fine tune. It's really quick to do each of these iterations. Now the model size is about 1 gigabyte in size, right? That's really pretty small. And when it's running in memory, it takes a total of about 2.3 gigabytes for doing inference. We also took Whisper and we fine-tuned it. We took the base model, 74 million parameters, and I'll go over why we fine-tuned it. And then that model size is approximately 150 megabytes, right? It's FP16, 2 bytes per parameter. And then total while it's running is 400. So in total, these two models together are running about 3 gigabytes. And then depending on what you want to do, you can, with the fine tuning, we're using LoRa, low rank adaptation. You can actually have, if you choose not to fuse the models or have different LoRa's, you can load different ones for different use cases. Okay, so let's get into some more of the details of how we built it. So one of the first things we had to tackle is really this function calling, or how to do tool use, right? We saw in the spring, right, with model context protocol, right, and agentic AI, being able to have agency with these AIs has become really popular. And then you saw, early models like Claude and, OpenGPT, that those very large models have the ability to do tool calling. But most of your models, especially your smaller ones, don't have that ability. So we actually have to add that functionality into the model. And then we're going to talk about what that means. And so we're also trying to make sure, what is the problem statement we're trying to solve? We want to interface with a natural language, right? The first step is going to be a model selection. What are they asking? Is this something we can do locally, or is this something we're going to go out into the cloud for? And then, makes sense, right? We are working in a limited resources, and that always is a consideration with whatever we're doing. So the first thing we're going to do to talk about function calling is really about synthetic data generation, right? And so what we need to do is, say we're going to take and make 1,000 training with a 200 test data set. How are we going to build this? So in this case, these models don't know anything about calling tools. So you actually have to teach it what a tool specification is. What are parameters? When do you choose to use that tool, right? And then, not only that, it's got to generate valid JSON information so you can parse the results. And so what we need to do is we flip the question around first, and we use these very large language models. Like in this case, we used Claude 4. We said, okay, given this tool specification, write me hundreds of different ways I could ask in natural language, given all of the rules to the game, given all this kind of strategy. Give me 200 cases of how I would ask that would end up using this tool, right? And this is how you start training. And for every one of your APIs, you're going to do this. How is it that what are the kind of conditions you will call to call this tool? And then going through, you have to train it to use parameters. What are valid parameters, right? A lot of it's querying the game state, but you want to change game state. And again, iterating the fact that it needs to respond with valid JSON, so you can kind of use this. And then again, in a lot of the strategy, you get into the details of it, is that you really understanding what that tool spec looks like is important, and something you have to think about. Models do better when you have a single way of doing something. Don't add confusion. These models get confused really fast when they're small like this. So have very explicit function definitions that the model can know exactly what it does. And try to really limit what each function call does. Have it do one thing, right? And this is true, even like you see these large language models, they do really well with things that are really simple. Go turns out to be one of the best languages that large language models generate. But C++, because of just how chaotic it is of a language, actually is really quite difficult. And that's true. Once you get to these smaller models, you have to take that into consideration. Next thing, just a little bit more about this function calling, right? So think about all the different scenarios you have, right? You have single function calling. Okay, that's really simple, right? Hey, what are my villagers doing in this case? And it's like this light from Pixar. And then, so another case is, what is like this multi-function steps? Like, hey, I want to get me a hotel and a flight from Boston to London on November 1st. And another example, right, is this multi-turn conversations where, hey, I want to go to London. What are my options here, right? And so there's, these are all the types of ways that people are going to start interacting with you and talking. And then another one is parallel functioning, like say, hey, get me a hotel and a flight for these dates. it can do those separately. It doesn't have to do them in series, right? It needs collectively to get all of the data, but they are separate functions. And then the last one, which is really makes sense, is handling missing information. This is key. Like, hey, I want to take a trip. That's missing a lot of information that you want your model to ask, because someone playing the game is going to be really quick in interacting, and it may need specificity in asking, into kind of resolving what you're asking for. And another part of this you don't really think about is the size of this context window, is like how many tokens is your input? And that's really key here, because you don't really think about it, but like that size of your context window, it really depends on how fast your model is operating. But also these small language models get confused. So if you give them too much context, they're going to get lost in the sauce. And they're going to like, hey, maybe I need to call this tool, help me answer this. And then it kind of gets stuck. So kind of balancing that context, size of the context, as well as the historical data. When you're playing the game and you say, hey, get me this villager information, that information is only valid for that moment in time. So if you just have your conversation history, like you think of it, and it's got, hey, I asked for what the villagers were doing at this moment, and then I asked it in this moment, and they're different values, the language model doesn't really understand time that well. It's not going to differentiate very well. It's just going to see it as a whole collection of information. So when you have information that is differing, but it's the same thing, the model can get confused. So you're going to want to have a strategy to think about this as how you are going to manage your context and your history. Okay. And quantization, right? And I mentioned this already, right? Quantization is reducing your numerical precision while trying to preserve the quality of the responses, right? Like, what is the performance? And in this case, we were able to reduce from the floating point 16, 2 bytes, down to mostly in 4 with a little bit of in 6, right? So that's a 70% reduction. But what you don't think about when you're thinking about, hey, I'm reducing this, I'm losing precision, and there is some reduction there. A lot of these models are trained with 32-bit floating point, and that reduction down to 16 is really imperceivable at this level. But as you go down to 8-bit and even 4-bit, you're going to see some degradation, and you need to make sure that in your training and your testing, that degradation is acceptable. Right? You're doing a LoRa, so there is going to be some loss. But do you care? Maybe not, because this is the scope of your problem, and these models are meant for really wide data sets. So if it has a catastrophic loss on something you're never going to care about, that's fine, right? So it's really like understanding the boundary and the shape of your problem set, and then testing for that. And as well as something you don't think about is that when you're doing that 70% reduction down to 4-bit integers, we're reducing the model from running at 3.4 gigabytes to 1 gigabyte. And that's probably your biggest implication on how fast this runs. Because your phone, right? It's not your NVIDIA on your desktop. It's only able to do, say, let's just say 50 gigabytes per second in memory transfers. So your 1 gigabyte model, that transfer for all of your tokens is going to be 20 milliseconds, right? And so now if you triple and quadruple that, it's going to go from 20 milliseconds to 50 milliseconds. And that's going to have a significant impact on this number of tokens per second. And that's how we're going to get to measure this, is that 20 milliseconds as you transfer, let's say with your KV cache and all your activation computation, right? It takes 30 milliseconds. That's telling you that you're able to manage 30 tokens per second, right? And that's a measure. And that also goes back to the equation of, well, how much do I want to have in my context? Because the bigger the context, the more tokens you got to process. Which even then goes back to the equation of, what do you do for prompt engineering? Everyone talks about, hey, you can do so much with prompt engineering, but you can tell what the cost is when you're on these edge devices. Because you're going to choose. And in the case, what we did is you're training using this fine tuning the rules of the game, the strategy to play the game. And that's because you don't want to put that in your prompt engineering and pay that cost every single time that you are going to be asking this model for inference. Okay. One of the things we touched on, and this is, again, we're doing a lot of work with a number of groups within AWS. One of the people, Aaron Brown, who helped write us a paper, he works in the automotive space. We get the economies of scales that we have a number of groups that are all kind of doing this edge work, and we're working together. And this is something that's important to gaming, but it's also important to automotive, which is fine-tuning the automatic speech recognition. So in our case, right, we're using Whisper-based. It has 74 million parameters. And it's been trained on a lot of languages, but turns out that at that level, it's, in this case, what we're talking about is like Japanese really wasn't that great. So you are going to want to say Japanese, a very important language within gaming. We fine-tuned for LoRa to be able to do Japanese. Because Japanese, turns out, right, you got 3 writing systems that are all intertwined. They can be used within the same sentence, right? Hiragana, katakana, and kanji. The Japanese doesn't have discrete word definitions. So, that's important. That's a thing. And then also, you can have, pronunciation of one word can have different spellings based on different context and have entirely different meanings. So you got to be able to handle that and fine tune that. And so we were able to do, use the common voice data set and to create fine tunes for that Japanese. And so this may be something that you need to do where you have a number of these LoRa's, and depending on what your audience is, you load in these LoRa's for those languages, especially for your pictorial languages like Japanese and Korean. And another thing that's not quite obvious is that for your small language models, and this is true for large language models, the first phase is that tokenization of that natural language. Tokenization of your pictorial languages turns out to be really expensive. English turns out was kind of the first language of choice on these. And so what you say in English turns out it takes like less than half or a third the amount of tokens on your input to your language model than does Korean. And that matters on the speed on how these systems process. And these are all considerations you want to think about when you're working in this space. Okay, real quick, we'll go, I'm not sure how we're doing on time, but here, real quick, what we're talking about is on the edge device, right? We're doing, speech to text. And then we have our classification system that's again, that model, we're using this model, we can load LoRa that specializes in, is this something we can handle locally? What LoRa's it needs to do that? Or is it something that we need to send to the cloud? Or, maybe you're using a little bit of guardrails and you're like, no, I don't know how to answer that. And then if it stays locally, it goes to the local SLM and then generates it back into speech. But the pink icon there is your collection of data. And this is always really important, is what is that feedback? So what we used is OpenTelemetry. This is an open source data collection system using servers. It gets your logs, gets your metrics, gets all of your traces. And AWS has a collector that collects all of this data. And then you're going to want to send it up to the server, because even though you're thinking about, hey, running this model on my device, you really have to think about the long-term ecosystem of supporting your game. The game changes, the models change, the way people interact with the model is changing. And so then on the next side, on the server, right, you're going to use the plethora of AWS services really supports this, and it's a great go-to for everything from your REST interface all the way to creating an agent using what's called agent core, and using Bedrock and S3 vectors to kind of have that response when you need to go to the server, or you're collecting all of your metrics, your logs, and you want to process them. You want to process them for a number of reasons. One, Maybe you're using a managed service like Prometheus or Grafana, so you can get some visual insights into what's going on with your device. Is it running slow? Any of those kinds of questions. And then again, you're going to take all that feedback because you're going to then use, say, something like SageMaker, which is end-to-end enterprise-grade, ML ops, everything from versioning and testing and all of your data engineering tools, so you can keep iterating on these models. Work great in the lab, put them out in the field, you're going to be iterating. And one last thing. So again, model feedback, right? And as I said, you have this continuous loop of refinement, right? How operationally, how well was it doing? And how do you measure success, right? You're going to find your players, as we all know, are very dramatic, right? And so what that means is they're angry. Are they angry at the game or are they angry at the AI, right? And so you're going to want to bringing all of that data back to be able to analyze that feedback. You're not going to be able to do it on the device, right? The complexities, understanding all of that. You're really going to want to bring it to these large systems and be able to do your, the deep dive into all of your analytics.
Cool. Thank you, Patrick. So to wrap this up, what did we learn through the experience and what will we do different next time? So did it work? Yes. I actually found it really interesting to both be doing things in the game with my hands, but also be able to send commands. So if you think of a strategy game, you're over here fighting a battle, but you want to check in on your farmers in this case, you can do that, right? You can just say like, hey, how are they doing? They should be farming. Okay, back to my attack. You don't have to scroll over to your base. And that it sounds like a simple thing, but it's actually really cool. And same way you can ask for help. There's a bunch of things you can do with this idea of like a second screen assistant beyond the core use case we just described. It also gives you a window to your game when you're not in the game. And so if you, for example, you're playing with friends, you want to schedule a raid, you can think about how that would be helpful. Maybe you do it through text messages or other services, but this assistant can go a long way. It can also handle translation. It can handle your socials. There's a lot behind this idea, kind of like in the expanded space of all the things it can do. Patrick talked through a lot of the challenges we encountered. I would just cover the mitigations. So context reduction, it's a big thing. Every token counts. Try to keep your context compact, small, and relevant. You can, to wrap this, actually, I'll get back to that. Things we learned in training the model, they're sensitive to change. So because of the low resolution, because they're so small, you'll probably take multiple passes at training them. And that's kind of what I mean about models becoming a game asset in the same way that the 3D model is, or a piece of code. Like you make one, it looks all right, maybe it makes some mistakes, you train another one, suddenly somebody's responsibility to make sure that the model works correctly, despite game changes, despite different devices, etc. Hardware considerations, you talked through part of it. So here's one thing we realized, is that, and it's related to feedback we also get from customers when talking about small language models. The feedback is often, oh, well, but I don't want to just target devices that can actually handle this model. Like not every phone's going to be able to take a 3 gig model in memory. But maybe you don't have to, because what you can do is fall back to either the same model running in the cloud and in a small Lambda, or fall back to some other cloud-based solution. And that actually opens up your potential install base for your game a lot wider, right? So now you're not just targeting devices that can support the game, you're targeting all devices with some degradation of the on-deviciness versus the cloud. There's going to be some trade-offs in cost, but it does give you those options. And so what could we do better? We could talk about local RAG. This becomes interesting. There's different ways to implement it. We could talk about that after the presentation. But it gets interesting when you need to manage the context based on some game actions. So maybe you talk to a character and you did a thing, you made a choice. That choice needs to be reflected in every future interaction. So gating the knowledge based on what's happening in the games, that could be one solution. Voice input, you mentioned detecting whether the player is angry. There are now solutions for detecting emotion in the voice. Our voice model, Novasonic, does handle that. So even if the players don't speak in complete sentences, you can infer a lot and use that as signals. And of course, all of this stuff is measurable and A/B testable. And so you can, there's skip over that one. We do have, just to mention this. So AWS, because we work with other industries, has a long has services that support IoT. So think of robotics, think of automotive, etc. There's a lot we can learn from the services that work in those areas to do with ML model deployment to a device, handling the resources, handling the versioning, handling compatibility between what the device is doing and what the cloud is doing, because again, all this stuff doesn't live on its own. And so really the takeaway for us, and like what we would recommend you think of broad strokes when considering in-game AI, generative AI, is think of like, you're gonna have a bunch of stuff running on device. It's gonna do some jobs. That's where the context is. You should do it. It's great. You're gonna have devices that don't support the level of resources that you need, in which case you can hop over to, for example, an SLM in your game server. That is a type of device. That can be a fallback. And you'll probably, realistically, if you're running games and you're versioning and you're updating games, you're going to end up with players running different versions of the model at the same time because they haven't updated to the latest. Think about that as well. But this whole stack becomes elastic because the job can be handled, ideally it's handled at the cheapest layer, but it can continue to operate in the not just